Hello, everybody. My name is Borzoo Bonakdarpour from Michigan State University. I'm going to talk partially about distributed runtime verification until partial synchrony. This is joint work with my students Ritam, Ganguly, and Anik, Momtaz. So let me first motivate what the idea is. We are interested in runtime verification, which basically means a monitoring mechanism where the monitor inspects the execution of a system and evaluates that with respect to a formal specification. This formal specification is usually in terms of some temporal logic, regular expressions, or some finite state machine. Now, in this particular work, we are interested in distributed RV, where one or more monitors observe the behavior of the system at runtime, and they collectively want to verify the correctness of the system at runtime. Now, in distributed RV, one of the challenges is that the processes that we want to monitor, they do not share a global clock. And that means the order of events that happen in the system cannot necessarily be, it cannot be ordered. The order cannot be determined. So for instance, look at the figure on the right side where we have processes P1 and P2. Process P1 hosts a variable x1, process P2 hosts a variable x2. The initial state is 1, the value is 1, 2 respectively. Then in process 1, x1 becomes 0, x2 becomes 0. And let's imagine the formal specification of the property that we want to monitor is that next, that means in the next state, x1 plus x2 is strictly greater than 1. Now, these two events, that mean x1 equals 0 and x2 equals 0, are concurrent with each other because they cannot be ordered. And depending on which one actually in the physical time happens first, we can have two different verdicts. So for instance, if x2 happens first before x1, then this property is false because x1 plus x2 is equal to 1, which is not strictly greater than 1. On the contrary, if x1 equals 0 happens first, then x1 plus x2 equals to 2, which is strictly greater than 1. So as you can see, even in this very simple example, depending on what order of events we consider, there can be different verdicts for the evaluation of our specification. Now, enumerating all of these possibilities is not practical at runtime. It's not even practical offline. So the question is, what do we do? We are not the first who worked on this problem. The Vijay Garg looked at the predicate detection problem for a long time. He has this notion of slicing, which is very well established. This is in a fully asynchronous setting. In my group, we also looked into decentralized runtime verification for LTL specification, even again in a completely asynchronous setting. The main problem with a complete asynchronous setting is that it doesn't scale well. Now, in the synchronous setting where all the processes assume a global clock, there is also some work on monitoring LTL specifications. But the problem with this line of work is that in a large distributed system, it is not possible to assume a global clock. Now, more recently, in another paper which was published in the Runtime Verification Conference in 2017, there is a notion of partial synchrony that was used in order to do predicate detection using SMT solving. So now what we are going to do is we are also going to adopt this notion of partial synchrony, where we employ a clock synchronization algorithm that ensures bounded clock skew epsilon between all the clocks. And this is going to limit the level of non-determinism in the system. So if you look at the figure on the right side, there are so many concurrent events if there is no such a clock. But if we have a clock synchronization algorithm that guarantees bounded clock skew of epsilon, then in this area of the computation where we have four concurrent events, that means E3 would be concurrent with E2 and E23 and E24, and E14 would be concurrent with E23 and E24, and again the same for E23 and E24. Using this scheme of a bounded clock skew would limit the window of non-determinism to only events E13 with E23 and E14 with E24. So our conjecture is that by employing such a mechanism, we can limit the level of non-determinism and we can do monitoring in practical settings. Now I'm going to hand it over to my very talented students who will give the rest of the talk.
Thank you, Borzoo. Now for the preliminaries, first we go over the LTL. We are not going into the details of the LTL semantics, but here we have three examples of temporal operators. The first one being eventually P, which says that P should appear sometime in the future. The next one is globally Q, which stands for Q should hold at every state in the trace, and P until Q tells a trace, represents a trace where Q is true in the future and P should hold at every state before that. Now LTL is defined for infinite traces, but in context of RV, we need something to do with finite traces. But so that's why we have a three-valued LTL, which represents the verdicts as a set of B3, as a set B3, whereas top, bot, and don't know. The top or a true represents a formula that is permanently satisfied. A bot or a false represents a formula that is permanently violated, and the unknown represents a trace that can go either wise. For example, we remain in the don't know state until we see a P in the future for eventually P, and once we see P in the future, the verdict goes to top. For globally Q, we remain in the unknown state because we can always see a not Q in the future, and that can make the verdict go false. So that's why we remain in the don't know state. For P until Q, we remain in the don't know state for every P we see, and once we see a Q, our verdict changes to a top. Now here for a LTL3 monitor, you see we have a monitor for the formula A until B. Here we remain in the don't know or the unknown state for every A that we see, and we only move to the accepting or the top state for a B, and we can always go to the reject or the bot state for not A and not B. Now here is a distributed computation model that we have for two processes, P1 and P2. Each of the process can have local states. E1 and E11 to E14 are events of P1, and E21 to E24 are events of P2. There can be a communication between the processes as well. Here E12 is a sending and E22 is a receiving event. Now each event has a local time by the local clock of that process, and there is a maximum clock skew which makes all the events less than epsilon apart in the system. Each of the local events of each of the processes can be arranged by the happen before relationship. The happen before relationship also makes sure that the sending event happens before the receiving event. So we have a happen before relationship between E12 and 22 over here. And due to the clock skew, we also have some more happen before relationship between the events that are outside the epsilon window with the events that are inside the epsilon window. Happen before relationship are also transitive, meaning if E happened before F and F happened before G, we have E happen before G. Coming to consistent cut, consistent cut should have all the events that can be ordered by a happen before relationship. Here E11, E12, and E21 um, is a consistent cut, whereas since E11 strictly happens before E22, and since E12 strictly happens before E22, that's why this is not a consistent cut, the last one being also a consistent cut. The frontier of a consistent cut is represented by front C, and here E14 and E24 is the front of the shown consistent cut. Coming to hybrid logical clock, it is represented by a tuple of tau as the local clock, sigma as the maximum, seen global local clock, and omega being the causality. When there's a message pass and you see that the event in P2 changes its sigma from 0 to 10, since tau of P1 is 10 and the causality reflects the change. Same goes for the local event of P2, which is accounted for the changing tau and omega. Now this is repeated for all the other communication and all the other events in the system, and this also gives us few more consistent cuts that we see in the system. Just like C0 and C2 does not represent a consistent cut, but C is a consistent cut over here. Coming to the formal problem statement, we have given a distributed computation. We have a sequence of consistent cuts can be represented by the fronts of those consistent cut, and the evaluation of the LTL formula with respect to a distributed computation is based on the LTL3 verdict of that computation. The SMT-based solution will be taken over by Anik.
Thank you, Ritam, and hello, everyone. So now we're going to talk about the SMT-based solution that we have for the problem that we've been talking about so far. So given a distributed computation, our approach is to transform this monitoring problem into an SMT problem and then have an SMT solver solve this problem. In our approach, we have two SMT instances, one instance for the distributed computation itself and the other instance for obtaining all possible paths in the LTL3 monitor. So we start this by developing an uninterpreted function called row. And the purpose of this function is to give us a sequence of consistent cuts that starts from the beginning of the monitoring state and ends at the end of the monitoring state. So let's take an example on the right here where we have a distributed computation and we have two processes here. One process hosts the variable x, the other one hosts y. And then the formula that we want to monitor here is always x is strictly greater than y. So our row has to give us a sequence of consistent cuts such that this formula holds throughout the entirety of the computation. So the way we start off is we say we map row 0 to an empty set. And then we take either one of these events, that's up to the SMT solver, and then when row is 2, we take the first two events. And in this case, what's happening here is x is 3, y is 1, and the formula x is greater than y is holding here. So we take another event and then another event, and in all cases, our formula x is strictly greater than y holds. And then we reach the end of the computation where we have 9 and 7 and it still holds. So we do get a sequence of consistent cuts where the formula holds through the entirety of the cuts. But let's take an example here, and let's say instead of in the third event of the second process, instead of 5, let's say the value of y becomes 6. And in this case, let's say if our epsilon is as big as it is right now, the third event from both the processes fall within the window of epsilon. And since it falls within the window of epsilon, we can say that these two events are concurrent. And if they're concurrent, then x is greater than y no longer holds here. And in this case, our uninterpreted function rho will not be able to generate a sequence of consistent cuts that satisfy the constraints that we have given them. Speaking of constraints, now we're going to talk about the constraints that we're adding to our rho so that it gives us the consistent cuts, a sequence of consistent cuts that we need. The first constraint would obviously be that every element of rho must be a consistent cut. And the second constraint would be that in the current state, when we have a consistent cut, it must always be one more than the previous consistent cut. And then the other constraint would be the previous consistent cut will always have to be a subset of the current consistent cut. And another constraint that we have over here is we want to make sure that our running computation indeed ends on the last state, QM. And when our monitoring path does not have any self loops, all we have to do is start from the last state and then work our way to the first state. And if we do have loops and then cycles, then we have some methods in our algorithm where the cycles are converted into acyclic paths, and then we do a similar constraint there as well. And then finally, we make sure that our first mapping, rho 0, is indeed an empty set. And we do this for every reachable state in the automata so that every possible path is explored. However, we know that the RV problem is an NP-complete problem, and that means for a bigger computation, our runtime becomes exponentially large to the point it's no longer monitorable. So we needed to come up with techniques to optimize our algorithm or our solution so that it falls to an acceptable runtime range. One of such techniques that we employed was segmentation. So in this technique, let's say we take a computation like the one that we have over here on the example, and we take this computation and chop it up into smaller segments. And what we do is we consider each of these segments as an individual computation, and then we run our monitor on each of these computations, and we have SMT instances for each of these computations. But there's one problem here though. The problem is that there could be instances where a pair of events were concurrent in the original computation is no longer concurrent in the segmented computation. In this example here, let's say if our epsilon is big enough, then then event 3 in P1 and event 2 in P2 could have been concurrent in the main computation, but it will no longer be concurrent here because these are two separate computations after the segmentation. Same goes for event 6 in P1 and event 5 in P2. So how do we solve this? We solve this by increasing our segmentation to the point that it overlaps with its adjacent segmentations. And the increased amount is exactly epsilon, or our clock skew. So this ensures that any computation or any pair of events that would have been concurrent in our main computation will be concurrent in the segmented computation as well. Now we do another level of optimization where we harness the power of multicore processing in multicore architecture CPUs. What we do here is we assign each of these segments to each core of the CPU and then have it do its own solution, and then we take all the solutions and merge them together. But again, there's a problem here. So we solve this, the problem being that there could be paths that would remain unexplored if we take each of these segments and these segments have no way of communicating with each other. So we create a reachability matrix here, and the purpose of this reachability matrix is for each segment, for each state, it checks whether or not that state can reach all the other states. And if it can reach that state, then we say we mark it with true. If it can't reach that state, then we mark it with false. And then once we've created this reachability matrix, we create a reachability tree from here. And the purpose of this tree is to start from the starting state and then go to all possible states it can go to, ending at the leaf nodes or leaf states rather. And then with this tree, we can determine whether or not there exists a path that is unknown, whether or not there exists a path that is acceptable, or whether or not there exists a path that is rejecting. Now I'll pass the mic to Ritam again for the next part. Thank you.
Thank you, Anik. Now to go over the case studies and evaluation. Now, for first, we go over the experimental setup. The experimental setup is of two phases. The first one being the data collection phase, where we have a synthetic experiment and the one with Cassandra. The next phase is of the verification of the trace that is being generated in the data collection phase. We make sure that all the events that are generated are evenly spread out over the entire length of the trace. And the parameters that we are studying here are the number of processes, the computation duration, the number of segments, the event rate, the maximum clock skew, the number of messages sent per second, and the formula that is under monitoring. First, to go over the impact of assuming partial synchrony, we see that with increasing value of clock skew, the runtime increases exponentially. This is expected due to the more number of concurrent events due to a larger clock skew. With the change of predicate structure, we see that the disjunction takes more time than the conjunction. This is because to make a conjunctive formula false, we need to have any one of them false, and that makes the entire formula false. But for disjunction, all the sub formulas needs to be false in order to make the formula false. This accounts for more time. Going with the LTL formula, we see there's a linear amount of more time needed for formulas with more automata depth. And we see that for increasing segment length, the runtime decreases at first, but then bottoms out due to the overhead of creating the SMT encodings in our monitoring solution. Now, next we have Cassandra. Cassandra is open source distributed NoSQL database from Apache. And since Cassandra does not implicitly support normalization, we thought it would be a good way of having normalization in Cassandra using runtime verification. Here we have two databases, one of student, the other one enrollment, and we make sure that we don't have read write or a write or a delete anomaly in the database in Cassandra. With parallelization, we see that increasing number of cores decreases the runtime by a hefty amount and then bottoms out due to the time needed for the SMT encodings to generate. And the other one shows that with event rate of 1 and 2, we kind of break even for even number of processes as high as 9 on 10. Now, the big question is how realistic it is. Now, we have tested our solution for two scenarios. The first one being the extreme load scenario, which represents something like Netflix, where we see 1 million writes per second. And the next one being the moderate load scenario, which represents Google Drive, which only allows 500 requests per 100 seconds per project and 100 requests per second per user, which kind of boils down to 5 events per second. And using the graphs, we see that we are we are doing good in the moderate load scenario. Coming to future work and conclusion, so the notable improvements of our work will be we are the first one that is using partial synchrony. We achieve a great deal of scalability by SMT encoding, and we are making sure we are not losing out on any verdict, as well as parallelization using multicore optimization. Looking forward to the future work, we hope to scale up our technique to monitor cloud services and have a trade-off between accuracy and scalability. For distributed RV, we aim to have a distributed runtime verification technique for timed temporal logic and for continuous signals in cyber physical system like stream runtime verification or something like that. That's it. Thank you. Have a good day.